Okay, I'm pretty sure that you know that there's a midterm coming up on Thursday, and therefore today I will devote this presentation to, let's think about it as a review, but it's really solving several problems that may help you to focus on what you need to do on Thursday. Okay. Yep. So let's look at the first problem, and this is not a simple pendulum. It's called a compound pendulum. Because simple pendulum traditionally refers to a ball attached to a mass, a spherical mass, for example, attached to a pivot point through a massless rod. But this is more complicated. The rod is not massless, it's actually distributed. And if we ignore damping, we lift this thing up, we let it oscillate, it's going to go back and forth forever with certain frequency. So we like to find that frequency, and the first step in doing such problem is to find the mother of all equations. In other words, the governing equation which describes the motion of this oscillating object. As the degree of freedom, we're going to use theta because specifying angle theta will tell you exactly where this compound pendulum is. So theta is our degree of freedom. And then let's say that the mass center is at some location which is denoted by G, the distance r from the pivot point. The next step is to draw the free body diagram. So the only forces that are acting is the gravitational force and the unknown reaction force at the pivot point. So what we do is let's assume that this either J about O or I about O is the mass moment of inertia of this distributed object about the pivot point O. So the choice of using JO or IO, it's up to you. Generally speaking, JO is reserved for problems involving the torsion. But anyway, either way, so I will use IO here. Okay. So from a second year dynamics course, you know that for a simple planar motion that we have here, sum of all the moment about any fixed point is I about that fixed point, I about O, times angular acceleration, which is theta double dot. Okay? So let's see now. About the point O, this one has a negative moment. R about O, of course, is R about O is 0 because it goes through O, and therefore you write down the expression for the moment is going to be mg times the moment arm, and moment arm is actually this r times sine of the angle theta. From trigonometry, if you look at the distance from O to the extension of this line, the force, the moment arm is right there, and it's going to be r hypotenuse times the sine of that angle. You just clean it up, and if you assume that there's a small scale oscillation, so sine of theta is approximately theta, then you get the mother of all equation for this problem. And of course, you recognize this thing as basically the mass or effective mass, and this thing as a stiffness or effective stiffness. And so the natural frequency is going to be the ratio of stiffness over mass, or effective stiffness over effective mass. So mgr over I about O. Okay, so that's our first problem. This problem we have done before, except that I have springs at both ends. Now at one of the ends I have a damper. Again, the simple degree of freedom to use here is the angle theta, which depends on time, of course. And so what we're going to do is write the sum of all the moments about the point O, fixed point O, equal to mass times acceleration, or effective mass times acceleration. And from dynamics, you know that this is I about O, or here is J about O. I changed this J to I because this drawing comes from I think Inman's book, and I just decided that instead of J, I would use I that you may be more familiar with or comfortable with. Okay. Now notice that point O is a very convenient point because we don't have to know what R is. R is an unknown reaction force, and if you take moment about O, it just go away because there's no moment about O. Now, what are the forces that are acting here? There's a spring force, which if theta goes down, let's assume that theta goes down, the spring force opposes that. And so both spring and damper actually oppose the motion, okay? And the force of uh, the spring is the displacement of the spring or compression of the spring, which is incidentally approximately b times this angle theta. So in this right triangle, assuming small angle oscillation, so this compression is just b times tangent of theta, but tangent theta is approximately theta. So we are using small scale approximation. Now, as far as the damping force is concerned, it is proportional to the velocity. And if you just look at, for example, the stretching of this damper is going to be a times theta, okay? But since we're talking about velocity, it's going to be a theta dot. So the damper's velocity is actually a theta dot, okay? A theta dot, okay? And times c, and just write all the counterclockwise or clockwise moment taken as positive. So this is counterclockwise negative. These are both negative. So they have negative moment because you can see that they're counterclockwise. Now, if you clean it up, you're going to get the mother of all equations here. As I said, some of you may prefer to write this thing as JO, but I'm using IO. Now, basically, this is the effective mass, this is the effective stiffness, and this is the effective damping coefficient. So we can use all our formulas. So natural frequency is square root of K over M, of course, K effective over M effective. Effective damping coefficient, critical damping coefficient is 2 square root of K times M, but of course, K effective times M effective. And the damping ratio is C effective, whatever it happens to be, divided by this guy, which is C effective critical. Now, so anything that we have done before, and it involves such as things as mx double dot plus cx dot plus kx equal to 0, anything that we have done before applies. For example, we assume that there is an initial displacement, so there is an initial angle. We assume there is an initial velocity, so we assume there is an initial angular velocity. So all the formulas which we have done in the first 2 weeks of the course for the solution of the mother of all equation applies with this identification. And the same thing that we did before is applicable. In other words, zeta less than 1 involves oscillation and damping, a damped oscillation. So it's under damped situation. Zeta bigger than 1 is the over damped case, and zeta equal to 1 is the critical damped case. Let's do this problem. Very simple. You're given two cantilever beams right in the middle. The details of the beams are given here, different material, possibly even different length. So we have a mass attached in the middle, and if we remove the mass and let it go, this whole thing will go up and down as long as there is no damping forever. So without damping, the mother of all equations is going to be mx double dot plus kx equal to 0, free vibration, okay? It's just a matter of finding the k, the fancy k for this configuration. So the cantilever beam on the left acts as a spring with this stiffness. Remember from deformable bodies and the things that we did in class, in vibrations class. And the same thing can be calculated for the right-hand side. And these two both resist simultaneously the motion of the mass, so they're in parallel configuration. And I'll just add them up. and then the rest is history, because you just write down the expression for m over k. M, you're told what it is, 165 kilogram, and k we just found. Of course, just remember this now is k over m, right? Not m over k. K over m, and you get that many radians per second. We're going to solve this problem. This is also the essentially that mass spring damper system. Assume there is damping, for example. And the only thing is it's a system, torsional system, okay? So this guy, this shaft with the appropriate dimensions, whatever they are, give and the shear modulus material properties will give us a stiffness. And we have done that before. It's coming from GJ over L type of thing. Remember, for axially member, loaded member, the effective stiffness of that is AE over L. For torsion, GJ over L. But anyway, what you want to know is here's the data that we have. You're given the value of J, because this is torsional, it's written as J, no problem. And if we calculated the stiffness of this fancy bar based on the material properties and everything, suppose it comes out to be K equal to 400, and C is given. And what we like to know is if we initially twist this thing by 5 degrees and let it go, what would the angular position be after 100 seconds? The moral of the story is that you have to beat this thing to death. You have to find a solution for the mother-of-all equation as a function of time given the initial condition, and then at the end plug in the value of t equal to 100 seconds. There is no shortcut. So first of all, here's the mother-of-all equations, the torsional problem, J, C, and K. And remember, this C is, of course, is going to C is the torsional damping. Okay, this K is a torsional spring, etc. And J, if this is a disk, is 1/2 mr squared. Okay, so, but anyway, if we write it in the simplified version, it's right there. We just have to plug in to calculate natural frequency, square root of k over m. Remember, but we don't have m, we have a torsional system, so k over j, that's this. And we can find the damping ratio. It's just the different ways of writing it. You can write it like that, or you can write it like this, etc. And it comes out to be 0.0158, which means it's an underdamped problem. It involves oscillation with decaying amplitude. Now, in order to write the solution, we need the damping frequency, which is given by, the thing that we know already, and works out to be this. And now we go get the mother of all solutions. Remember, this is a damp-free vibration. The solution came out to be like that. We have to find big A, and we have to find phi. Everything else we know here. And there were formulas for big A and phi. Remember, there is an identification between x naught and the theta naught. They are the same. And v naught is theta dot. Okay, so this is for translational motion. It also applies to rotational motion, as long as, of course, you make the appropriate identifications right there. Now, for us, this one is 0 because it says that you twisted it by 5 degrees and then let it go. So converted to radians 5 degrees, and theta dot is 0, released from rest condition. And it's just a matter of plugging it in this expression, and you have your solution. You have the whole thing right there. All right. Now, if you want to get the angular position after 100 seconds, you just plug in t equal to 100 here, and you work out the number, and comes out to be approximately 1.7 degrees from the initial equilibrium position. Of course, the answer is going to be in radians, because everything here is in terms of radian. But then if you convert it to degrees, it's going to be 1.7. You can see that it started from 5 degrees and it oscillates and damps out to 1.7 degrees as amplitude. Now I've also done the plot of this theta for you here. You can see that, and using MathCAD, I've done this thing, my favorite package. All right. This problem is taken out of Rao's book. Essentially, we are interested in the torsional vibration of a propeller shaft. Okay, you can think about this thing as a, I mean, it's not a propeller, but you can think about it as something like that. Okay, I made out of steel, and for steel, this is the shear modulus. Basically, we have two springs. Here's a formula. You plug in the value of this piece from the first piece is going to involve the diameters of the inner diameters and outer diameter of this piece. Okay, there we are. And that is the length of the first piece from 1 to 2, and then do the same thing from 2 to 3. And these are in these two springs are in series. Even for axial loading, when the springs were like that, they would be in series. Okay, if they were parallel to each other, they would be in uh, what do you call in parallel. Now, if this mass was right here, and this end was fixed, if this torsional mass was here, and that right side would fix, then these would be parallel. So it was a slip of if this guy was in the middle and the right side was fixed, then uh, these two torsional springs act in unison, and they will be parallel. Just add them up. But here, of course, you can see that because they're in series, the stiffness is smaller than them individually. If you get this number, it's less than that, and it's less than this. All right. Let's do this problem. It says we have a helical spring. Now, these kind of things are what you are going to be studying in your machine design courses, or you already did that, your fourth year student. In your machine design class, probably. Now, so we have formulas. We have formulas for finding the stiffness of such things. If we have material properties and dimensions and everything, and so we can find torsional stiffness, but or an axial stiffness, by the way. But the problem is something else. It says consider designing a helical spring such that the attached mass of 10 kilogram, the resulting mass spring oscillation has a frequency of 10 rad per second or 1.6 hertz. Okay, so well, first of all, if you're talking about uh, axial stiffness of that, if you're talking about axial stiffness of that, we have to write uh, the axial, the formula for machine design, which gives you that. But this this is actually that value from machine design uh, textbook. You can find that the axial stiffness the axial stiffness of this helical spring is given by that. Now, what are these things? G is the shear modulus of the steel, which is right there. D is the diameter of this wire, which is wound together to give this helical spring. And R is the nominal radius of the helical spring. In other words, this is R. See the mouse? This is our mouse cursor. This is R, and N is the number of windings. Okay. So first of all, we are told what the natural frequency is, and we know what the mass is. We're told that the attached mass. Okay, we're told the attached mass has a mass of 10 kilogram, and if you let it vibrate, this is what it did. So we get the stiffness of that. We got the stiffness based on frequency and the mass. We get the stiffness, and then we go and you know that the left hand side is 1000. Okay, So this is what you got. You have to make some choices here. For example, the G we know is the shear modulus, which is right there. Now, you have a choice on diameter, number of windings, and the mean radius. So those are your choices, okay? And uh, that's why it has many solutions. Diameter of the material, radius of the coil, or the helix, and of course, n is the number of windings. So let's say that the diameter of the material is 1 centimeter, okay, which is not unreasonable for heavy-duty helical spring. So we just plug it in, you're going to get that. You still have n unknown and big R is unknown, okay? So this is what you got, and then you have to make some decision. Assume a 10 centimeter radius, which once again, you have seen it probably underneath trucks, these transport trucks. This is 10 centimeter, okay? It's unreasonable, not unreasonable. And you're going to get 6 windings. So the moral of the story is that if you use 6 windings of a coil with 1 centimeter diameter, and you wound it so that the radius of this coil is 10 centimeters, the resulting spring will lead to frequency of 1.6 hertz if you attach a match mass 10 kilogram to it. So it's a design problem. All right, so let's do one more simple problem. We have a machine. The mass of it is 1.95 kilogram, and it's this is immersed in a viscous fluid, and determine the damping coefficient, in other words, C, when a harmonic exciting force of, when this is applied, when this is harmonic force is applied, and it results in resonance amplitude of 1.97 with that period. Okay, so first of all, let me restate this problem. You have a mass sitting in a container which is full of viscous fluid. Okay, and on this mass there is a harmonic force acting, and we know that when the frequency omega is at the resonance, in other words, this omega matches the natural frequency, then the amplitude is going to be 1.27 centimeter, and the period of oscillation is 0.2. Okay? So first of all, when we have the period of oscillation, we have the natural frequency. Okay? So this piece of information will tell you what natural frequency is. But let me also remind you that when we have a resonant condition, in general, of course, in general, if you have a harmonic loading applied to a mass spring system, damper system, okay, the position of the block as a function of time is given like that. We did this thing in week 3 and we spent a lot of time on it. Okay. Now, we also found out what this big X is and what theta is. Okay. Generally speaking, big X was given as that. Remember, this fellow was called the amplification factor, by the way, and uh, we are told that this period, this is the period of oscillation. Out of that, we can find a natural frequency, and it's going to be equal to the frequency of the applied load. So there, this is, yes, it is true that this is the natural frequency, but it's also true as driving force. That's why we have resonance. So this piece of information, 0.2, will tell you what the natural frequency is or what the driving frequency is, because they are the same. It is at resonance, okay? That's what this is saying. Now, what do we know here? So we know this omega n, we know m, we can find k, all right? And k comes out to be this number, okay? And once we know k, then you go and find the, uh, remember, we want to find c. Let's go find zeta, okay? Let's go find zeta, okay? So we just write everything in terms of this equation. See that? This equation, write it when r is equal to 1. And remember, we are told that when that happens, this amplitude is 1.27 centimeters. So there. So out of that, we get zeta. And once we have zeta, we have our c, because the definition of zeta is c over 2 square root of km, and just plug it in and you get your C. So there, it says determine the damping coefficient. That means determine C. Okay, let's look at another example here. We have an instrument, 50 kilogram, which is mounted on 4 springs, and the stiffnesses are given here. The foundation goes through a harmonic motion, up and down motion of frequency 50 rad per second, and this is the amplitude of the vibration of the, the, the ground, the base. So this is big Y, and I'm assuming this is in meters, so we're talking about 2 millimeter vibration of the base up and down. Now, the question is, what is the amplitude of vibration of this instrument? Well, first of all, we have the expression for the amplitude of the vibration of the instrument, big X, and we are assuming that damping is 0 here. There's no dampers there. So things simplify a little bit. We have the mass, we have the stiffness. There's 4 of them, and we get the uh, natural frequency, and we have omega base. Omega b is 50. So find the frequency ratio, you're going to get 2. Now notice that this frequency ratio is bigger than root 2. And if you go back to the graph that we had for the vibration base excitation, if the frequency ratio was bigger than root 2, actually the amplitude of the mass oscillating is less than the original amplitude of the base. And in fact, if we plug these things in here, we're going to get that the instrument actually vibrates at 0.6 millimeter instead of the base that is 2 millimeter. This is 2 millimeter, this is 0.6. And that doesn't surprise us because the R is bigger than root 2. R is 2, which is bigger than root 2. Now, the one thing you should keep in mind that notice that if you look at the value of R, the value of R is uh, bigger than 1, and therefore this quantity inside of it, if I didn't put these absolute values, if I didn't put these absolute values, it's going to be negative. And what that tells you is that the instrument is 180 degrees out of phase with the base motion. So basically, when the base goes up, the instrument goes down. That's something to keep in mind. Now we have another problem which involves rotational motion. We have done problems like this. The only difference is that this right-hand side is subject to a harmonic displacement. See that? Harmonic displacement. Okay? So we want to model this thing first of all, because we have to get the mother of all equations before we can solve it. Okay? Now, the details are given here. We know the mass, we know the stiffness. These stiffnesses we know, and the length of this. The length is 1, and the damper coefficient is 500, and the frequency of the driving force, driving displacement actually is 10 rad per second. Now, the amplitude of vibration of this point P is 0.01 meter. The first thing we have to do is to decide on the degree of freedom. We're going to use theta as the degree of freedom, so everything is going to be written in terms of theta. At the end of the day, we're going to have something times theta double dot plus something times theta dot, because we have damping, plus something times theta equal to a sinusoidal thing on the right hand side. Okay, and to do that, we draw the free body diagram here. There is a spring force here, which changes with time. There is a damper force here, which changes with time, and there is also a spring force uh, uh, which is pointing up. Actually, ignore this comment because I have fixed that. Okay. All right. Now, ignore this highlighted thing. I fixed that thing. Now, obviously, what you have to do is write sum of all the moment about the fixed point, O, the pivot point, equal to I about O, theta double dot. Okay, so let's do it. So first of all, this causes a moment, which is in this direction, opposite to the direction that we have chosen for theta. So later on, when we balance things, this is going to be a negative moment. It's a force, and then we have to multiply it by the distance, we get the moment. Incidentally, we are assuming small deflection. Therefore, you notice that the moment arm here, the moment arm about O is actually this horizontal distance. Okay, but what we're doing, we are assuming angles are small, so that essentially this length is equal to that length. Okay, so the stretching or the compression of the spring is just the uh, L over 4. This is L over 4 times the angle theta, and you multiply it by K, you get the force. Now, later on, we have to do the moment, of course. For the spring on the right hand side, uh, let's see how does the spring on the right hand side stretch. Notice that the difference between the spring on the right side and the left side is that on the left side, one of them was ground, didn't move. But here, this point P is also moving. So when it comes to calculating the force in the spring, we have to take the distance, the difference of these two displacements. In other words, x of t minus your 3L over 4 times theta. Okay? Because these are both moving. Here, one of them was fixed. That's why we didn't have to worry about that. Multiply by K. And the damping force is just, C times V dot basically, and V dot is just L over 4 times theta dot. These are the forces. Now we're going to do the moments. Please ignore this this highlighted item. So we write the moment. Remember that this guy gives you a negative moment. This guy gives you a positive moment right there. And damping is also going in the opposite to the direction of the theta, and therefore negative. And we're using the parallel axis theorem in order to find the I about O, and the way it works is that remember, for a rod, if you assume this is a rod, the mass moment of inertia about the mass center is ml squared over 12. Okay, but here we have to, because the mass center is right there, and there's a distance of L over 4 to the center of rotation. So that's why we have to do an m. Remember, d squared in from dynamics. So d is this distance, which is L over 4. Just a matter of cleanup here. Okay. Now this is what we get, and notice that on the right hand side, I didn't get x. I got, because it's force and then converted to moment, I get k also popping up. So this is force. K times x is the unit of force, and multiplied by L, unit of moment. Okay. So here's the mother of all equations for this particular problem, and we plug in our values here. Uh, the amplitude is 0.1, So these numbers were calculated using MathCAD, for example. That's what I use. And this comes out to be that number. This is the effective mass, effective damping coefficient, effective stiffness. And this is your essentially right-hand side, which is we call F naught. Because remember, we have done things like this, where the right-hand side was a constant times cosine. So we're just replicating those formulas to get our answer. So pretty much just I calculated the see that here's the amplitude 7.5, see 7.5, and then we plug it in our formula for harmonic forcing on the right hand side, you know, those things that we derived in 2 weeks ago, and we have everything. It's going to come out the amplitude of the vibration. Amplitude of the vibration of that rod is this. And the phase angle, this is the phase angle. If you want to calculate it, it's 0.578. And we have to, because if you're going to write the equation, it's going to be the amplitude of the vibration, which is this number, 0.01311. And the phase we just calculated radians is this number. Okay? So that rod oscillates at, according to this formula. Okay? Now I've plotted it here. But I've also plotted the answer if the right hand, that displacement on the right hand side, instead of being cosine, it is sine. Suppose that we were told that on the right hand side, that displacement is not 0.01 cos 10t, but it's 0.01 sine t. Now, if all you do is you replace that theta in the expression for theta, this thing with sine, and you're going to get essentially the same curve, because for steady state response, you can see that they are producing the same thing. Now, of course, initially things will be different, but we're not interested in the initial disturbance. Okay. All right. So let's do our problem number 10, and here uh, there is a centrifugal fan which weighs that much. This is not the mass, this is the weight in pounds, okay? And it's rotating with an unbalance of 20 pound-inch. Now remember, rotating unbalance is m naught times E times G. Just keep that in mind. M naught E G. So m naught, mass of the unbalance, times E, the eccentricity, and times G, which is gravity constant. But anyway, all I'm saying is that what you see here is m naught E G. Okay, and it's running at a constant speed. So we have a centrifugal fan with that weight, and it's m naught E G is 20, and your operational speed is omega r equal 100 RPM. Okay. Somehow we know that the damping is 0.2. But what we want to do is to find the value of stiffness so that the force transmissibility is 10%. Okay. And once we know that, we're asked to find the transmitted force. Okay. All right. So first of all, that 1,000 RPM is converted to rad per second. All right. And this is the weight. See, this is the weight. There's the weight. To find the mass of that in this weird unit slinge, you take 100 pounds divided by 386. This 386 is just 32.2 gravity constant times 12. That's what it is, because 32.2 is feet per second squared. Multiply by 12, you get this. But anyway, we got the mass here. Okay, and we were told that m naught times E times G is 20. Okay, m naught E G is 20. That means we can find m naught E. Now, we don't need m naught E to answer the first part, in other words, finding the spring constant. But to find later on the transmitted force, we need this number. I'll calculate this thing for you, but I don't need it to get the answer to the first part. Okay, so we go to the formulas that we know. Look at the formula for the transmitted force, the magnitude of the transmitted force in a rotating unbalanced problem. It looks like that. Now remember, this omega n squared times r squared, you could have also written it as er squared. This is the same as that. The difference is that this combination, if you want, you can write it as omega r squared. And the reason is that r is actually omega r over omega n. Okay, so we are told we want to calculate that k that is unknown such that this thing is 10%. Okay, notice that I don't care about what happens here. I don't need this. All I want is this thing to be 10%. That's why I said that this information is not needed to calculate the force transmissibility, because the force transmissibility is simply big FT divided by that, and it's 10%. Okay? So it's an equation, not a nice clean one. You can put it in MathCAD or MATLAB or something like that, and you get the value of R. And once you have R, you know omega R, right? So write down omega n is omega R over R. Omega R we calculated, just right here. And R we just calculated, magically calculated. And that will give you the value of K, which is 210 pound per inch. Okay, now, for the second part of the problem, the actual value of f of t, I need this coefficient. Okay, so ft is equal to this m naught e. We got the m naught e. It was this. We just plugged it in, and r squared right there. See that? R squared is right there. 105 squared, and we said that we want this thing to be 10%, so it's 10% 0.1, and we get 57 pounds. So this is the transmitted force due to that rotating unbalance. Okay, our last problem is a rotating unbalance problem. We have a machine that's 100 kilogram in total mass characteristic, and is supported by a spring here whose stiffness is given there, and there is a rotating unbalanced element which results in a 350 maximum 350 Newton force uh, on the support at the speed of 3000 rpm. Now this requires some explanation, and we'll come back to that in a second. Let's assume that we already measured the damping ratio, which can be done experimentally by pushing this thing down, let it oscillate up and down as a free damped vibration, and based on logarithmic decrement, we can estimate the value of damping ratio. There's two things you want to do. You want to find the amplitude due to this unbalance at that obviously rotational speed, and also how much force is transmitted to the ground. Okay, now this requires some explanation. What do we mean by a disturbing force of 350 Newton at that speed? Now, I want to remind you that rotating unbalance, when we treated the subject, it gave the same equation that we had when we had a mass, spring, and a damper subjected to a harmonic loading. Okay? In other words, we solve the mother of all equations, which is mx double dot plus cx dot plus kx, equal to F naught, for example, cosine of omega t. All right? Now, or F naught sine of omega t. And we knew everything about it. Then we came back and derived the equation of a unbalancing of a rotating mass, which came up with, again, the same left-hand side, mx double dot plus cx dot plus kx equal to the right-hand side is also of the form f naught sine omega t or f naught cosine omega t, but f naught has a very special form, and it was m naught times e, the eccentricity, times omega squared, or omega r squared, where omega or omega r is the rotational operating speed of this rotating component. So what this 350 is, disturbing force, is referring to F naught, which is m naught e m naught e omega r squared, or omega squared. That's what this thing is. That is not the force transmitted to the ground. Okay? So, first of all, we also use omega r and omega interchangeably. This is the rotational speed of the rotating component, or omega is the speed of that. Okay? Now, this is the disturbing force, F naught cos omega t, which for a rotating unbalanced problem, we showed that this F naught actually looks like this, m naught e omega squared. Okay? So that's what this thing is. That is not the transmitted force. So one of the things we have to do is to find the amplitude of the motion. In other words, we want the big X that appears in this problem. Okay? We had a bunch of formulas, and I'm going to review those again for you in the next slide. But anyway, we're looking for big X for a rotating unbalanced problem, and big F subscript TR for the transmitted force. Okay. For all of these, we know we need the value of R. Okay, so first of all, the natural frequency is root of 100 kilogram divided, the stiffness is here, 70,000 Newton per meter, divided by actually 700,000 Newton per meter, divided by 100 kilogram, and that gives you this radians per second. And we know what omega is, 6,000 RPM. Convert omega to hertz or radians per second and find the ratio of omega over omega n, and that's going to give you the value of R. Okay. Now, this was the equation for the amplitude of vibration of that machine when there's a rotating unbalance involved. Okay? And notice that what I can do is I can rewrite this in that way. Okay? And if you replace R as omega over omega n, this can be cleaned up. See that? Instead of R squared, we have omega R squared divided by omega n squared. This is what we called F naught in the previous slide. And this is the product of the mass of the machine, natural frequency of the machine is the stiffness of the spring. So notice that we have, if you look at this again, it is of the form amplitude equal to F naught over K, see, F naught over K times this thing that we call magnification factor, by the way. And this you have seen in chapter 10, before we even discuss the rotating unbalance, okay? And that confirms the fact that rotating unbalance is a special form of a mass spring damper system under a harmonic load. Okay. Now, when we did the rotating unbalance, we also found the expression for the transmitted force, Ft. Ft stands for the transmitted force to the base, and we had this expression. Okay, so this expression, once again, if you multiply both sides by the denominator of the left-hand side, you get this. But also keep in mind that omega n r is omega. Okay, so remember, r is omega over omega n. So r squared is omega squared over omega n squared. So either like that, or this, same thing. So if we want to find the transmitted force, we have to know this piece, and this piece is exactly what that F naught is. F naught times that expression. Okay, so these are the formulas that pop up in rotating unbalanced problems. And remember, this combination, the problem statement said this is what is referred to as disturbing force, which is 350 Newton. So we go and do part A. First of all, if you want to find a big X, and that was the plan, amplitude of the vibration of the machine, this is what you've got. Plug in the stuff that you know. You're told that F naught is 350. K was 700,000. Or we found zeta is given, and you get that many meters, or 0.0379 millimeters. Now, look, in this problem, they could have given us the value of M naught and R. M naught and E. And we could have calculated F naught, but they didn't. Okay? All they said is that disturbing force is of magnitude F naught, is of magnitude 350. In other words, if they had given us M naught, E, and of course we know omega operating speed, we could have found F naught, but they didn't give it to us in that form. They told us disturbing force is 350 Newton. Okay, there. Okay, we found it. And part B says, what is the transmitted force to the base? Well, there's a formula for it. We just did it. Ft is, or Ft over F naught is this, from the stuff in chapter 10. But we know what F naught is this. Or we actually know that F naught in this particular problem was given to us directly as 350. So that is what in chapter 10, or lecture 10, we call transmissibility, force transmissibility. We call this thing force transmissibility. But anyway, the moral of the story is that plug in your values. This was given to us as 350. This, we have the value of zeta and R. You just plug it in. And you get Ft equal to this number times F naught. So there we are. Actually, this is part C or part B. Makes no difference. So I don't have a part C. Okay. So Ft is F naught times this thing that from chapter 10 we call the transmissibility, obviously force transmissibility, and you get 47.89. All right, Newton. This is the force transmitted to the ground, and that takes care of this.